Okay, now let's see in practice how these different catalytic strategies come together to make a chemical reaction really go. And in many, many cases, this is going to be fairly common for many enzymes. I'm not going to say all for sure, because some enzymes will use subsets of those strategies. Some won't use elements of some of them at all. Others use absolutely every one of them. And that's sort of an example of what we're going to look at now. All right, and specifically what we're going to look at are the mechanism of the serine proteases, right? Some of you guys hopefully will remember some of this from your undergraduate biochemistry. And you'll remember, hopefully, that these enzymes, right, of course, can clip an amide bond. So what they're designed to do is to take an amide bond and split it back into its constituent amine and carboxylate group, right? Right? Okay. And they can do this really, really well. If you remember, I told you before that the spontaneous rate of hydrolysis of most amide bonds under a neutral pH can be measured on the year to a millennial time frame. Proteases, like the serine proteases, can take that hydrolysis reaction. So I should definitely mention that if you guys don't recall, that this is going to take an input of water. So fundamentally, this is a hydrolysis reaction. It can take something that's got to have a time constant in the range of about 3 times 10 to the 9th seconds, and it can make this reaction go in about 100 milliseconds, right? That's phenomenal, right? 10 order of magnitude sort of acceleration. That's huge, right? Okay, so the question is, how does this work? All right, and we're going to see, as I alluded to, the application of just about every one of those catalytic strategies, with the exception of metals in this case, to make this reaction really get going. All right, so just to remind you guys of some basic things about the serine proteases. If you recall, hopefully, you'll remember that the serine proteases represent, a large family of proteases. Actually, it's a large superfamily, and there are different subtypes that are put together in slightly different ways. There's of course, the trypsin and chymotrypsin-like family, and there are other families that have different variations in this theme, but they all kind of work in a similar-ish way, right? At least in the large first order details of the process, right? So you'll remember that here's our substrate, our peptide that's going to get clipped. There's our bond, the so-called cis-al bond that's going to be hydrolyzed. And if you remember, on the amino terminal side of the cis-al bond, which means the amino acid that's contributing the carbonyl group to the amide bond, there is where the specificity for the different serine protease rests, the ones that have specificity, right? Whereas trypsin, that so-called that N-1 amino acid, that side chain can only really be arginine and lysine. And if that amino terminal amino acid is proline, trypsin won't work, right? So sorry, if the amino acid that's on the C-terminal side of the bond is proline, even if there is an arg or lyse here, trypsin can't cleave. For chymotrypsin, of course, the specificity is different. Same basic mechanism, but the specificity is different. It recognizes peptides where that N-1 position is now a bulky hydrophobic, Phe, trip, and tire. And like trypsin, if the C-terminal amino acid, if that's a proline, it'll fail, even if the right specificity is there. And that has everything to do, that proline, the kink that a proline would put in here, mispositions some key aspects of the polypeptide chain, which is why trypsin and chymotrypsin can't chomp down on a peptide that has a proline in that position. Okay, now you guys maybe also remember some of the other things about this family of enzymes. Here's an example. This is a structure of, I believe this is chymotrypsin, if I remember correctly from when I put this together. Yes, this is chymotrypsin, right? And you'll notice here in this picture, right there, you see that hole right there? It's kind of like oriented this way. That's where the specificity of the readout takes place. It has to do with the character of what's in that hole, right? We'll see that in just a second. Then the key catalytic residues of the serine proteases, there are of course three. There's a serine, a histidine, and an aspartic acid, the ser-his-as, so-called catalytic triad of the serine proteases. All right, now I'm going to put this guy into rotation, get a little sort of a three-dimensional view here of what this guy looks like. Oh, no, it's not going to rotate. Well, okay, we'll go with it. In the case of the trypsin, right, that specificity pocket, this hole sort of penetrates back down into the structure. That's what the rotation would have shown you, but okay. In the case of trypsin, this hole is sort of deep-ish, right? It's just a sort of length to accept that extended methylene group of a lysine or an arginine. And at the bottom of that pocket, right, the shape of that pocket, as well as the charge, is sort of, there's negative charge enriched at the bottom of the pocket, perfect for ion pairing with a positively charged arginine or lysine. In the case of the chymotrypsin, remember the one that wants the bulky hydrophobics, the pocket is shallower, there's no more negative charge, and in fact, the pocket is now lined with hydrophobic amino acids that are now going to make those good hydrophobic van der Waals or London dispersion interactions with these hydrophobics, and the pocket shape is just perfect for those larger, bulky hydrophobics, right? Okay, so now the question is, how does this enzyme work? And this is where we put all these sort of pieces together, right? All right, so here's our catalytic triad again. You guys will remember there's the serine. That's going to be the key business end. The serine is our nucleophile that's going to get everything going. It's hydrogen bonded to this histidine, right? And then the histidine is hydrogen bonded to an aspartic acid residue. So notice these guys are not near each other in primary sequence, right? These guys are pretty far apart, right? 140 amino acids almost between the ser and the his, 50 or so amino acids between the aspen and histidine. So this sort of immediately, you think of this idea of how important it is to get the three-dimensional structure of this thing just right, because if it's not, these guys are mispositioned and not where they need to be for this chemical reaction to take place. So this is a three-dimensional problem. Okay, so here then laying figuratively into the active site of our enzyme, here's this is flipped around from the way I showed you in that previous one. Here's the carboxyl group. There's the amino group, the amide bond, right? The first thing that's going to happen is the serine needs to nucleophilically attack that carbonyl carbon to form a covalent bond, right? The serine alcohol group is going to attack the carbonyl to make a so-called, we'll see in a second, tetrahedral intermediate, right? That's sort of what it looks like here. So we've got, just right out of the gate, we've got several things happening that fall into these catalytic strategies. The first here, of course, is we're going to be doing covalent catalysis, because clipping that amide bond without providing an electrophilic sink for these electrons, when they come back out of that oxyanion to go somewhere else you want them to go, they would simply go right back down here. This would pop right back off, and you've done absolutely nothing, right? So the driving force in the absence of another sink for those electrons is just to reverse this and just spit the peptide back out. That's what you don't want to have happen. But to get these electrons to go where you want them to go, you've got to create this opportunity through this covalent tetrahedral intermediate. That's what that covalent catalysis is going to give you. The other key aspect here, because of the way the peptide lays into the pocket, where that specificity pocket is, the carbonyl carbon is perfectly positioned, both orbital orientation as well as distance, from that serine alcohol group for this to happen, for that nucleophilic attack to be possible, right? So we got a proximity and orientation effect there, right? The concentration of this alcohol group relative to this carbonyl, man, they're bonded right in there, a few angstroms away from each other. That's about as high a concentration as you could get these guys. So all of those things are happening in just this first step. But there's a key thing we got to get to go. We got to somehow coax that alcohol group to attack a carbonyl, right? You guys may remember from your basic organic chemistry, that is just not going to happen by itself, right? That alcohol group on its own is not an awesome nucleophile. And you got to do all kinds of things to coax a reaction like this to go normally. And in this case, the enzyme does it by using a little acid-base chemistry that is supported with some electrostatic stabilization. In this case, what happens is that hydrogen bond between the histidine and the alcohol group is thought to help polarize that alcohol, that oxygen hydrogen bond of the alcohol, help sort of beginning to abstract that proton. Now, there's a bit of a question here about how an imidazole with a pK of 7 manages to pull a proton off an alcohol with a pK somewhere around 14 or 15. Just from basic basicity alone, that shouldn't happen, but it does. There's been arguments going on for decades about exactly what happens in terms of, is this hydrogen bond here super special or something? I think this is still a somewhat controversial topic in terms of the down in the weeds of how these enzymes work. But the upshot is that this interaction between this histidine and that hydrogen bond is critical to get this to go. And there's something to the idea that this imidazole is helping pull that proton away from that alcohol, polarizing that bond so that this nucleophilic attack is much more efficient than it otherwise would be. All right. So when that happens, you're then going to begin to develop positive charge on this histidine, right? That's not necessarily something you want to have happening to a histidine at neutral pH, right? pK is a little bit lower than that under normal circumstances, right? It's not going to want to do that. It's going to want to throw that proton off. So that's going to be an inhibition unless you can figure out a way to stabilize that positive charge. And that is what the aspartate over here on the backside is thought to do. Its negative charge and its close proximity here is thought to help stabilize the formation of that imidazolium so that it is much more effective in helping polarize that alcohol and get the oxygen of the alcohol to attack the carbonyl. All right. So, example of electrostatic catalysis right there with our aspartic acid residue, some general acid-base catalysis right there with the imidazolium, and now here's our covalent catalysis. We made this covalent intermediate. Now, we've got to do something to get this reaction to move in the direction we want, right? But forming this tetrahedral intermediate, like I said, that's super unfavorable, right, in general. That's energetically expensive, right? This thing would really just love to come down in here and pop those electrons, instead of this way, right? This guy's come right back down here. This electron just pops, right back off, boom, and you just regenerate the serine alcohol and just let go of the peptide. All right. So we got to drop the free energy cost of forming that tetrahedral intermediate. And this is where the serine proteases come equipped with a feature recognition system, kind of like we saw with protein racemase, that recognizes a specific characteristic of this tetrahedral intermediate, right? Okay, so let's get a look at that. So here is sort of an idealized sort of blob of the trypsin, chymotrypsin, serine protease active site. Here's our serine, here's our alcohol, here's our histidine imidazolium, there's the aspartic acid residue. Here is that little cascade going on, the catalytic triad doing its thing, turning this alcohol into a good nucleophile, attacks that carbonyl carbon, and you'll notice something off here, off to the side. There's sort of a little hole, it's a little pocket. Not much there, right? Just hanging out there, but it's gotten a name. It's known as the oxyanion hole. And it's called the oxyanion hole because when the serine alcohol attacks that carbonyl, right, the bonding structure shifts, right? Again, from sp2 to a tetrahedral, right, to an sp3 like orientation. And that changes the geometry around that carbon. When that happens, the sort of oxygen kicks back sideways, right? Because the irresistible change in the electronic bonding pattern requires this geometric change. And there's a pair of backbone amides, right? Specifically one from the serine 195, one from other residues, depending on the protease, that are perfectly oriented and positioned to recognize the formation of and stabilize through hydrogen bonding that oxyanion of the tetrahedral intermediate. They basically catch it, right? And because they catch it and stabilize it through hydrogen bonding interactions that are enthalpically very favorable, that lowers the cost, makes it much easier to form this tetrahedral oxyanion intermediate, right? This is the so-called oxyanion hole, transition state stabilization, right? So that's an example of transition state stabilization that's based upon sort of geometric and charge features of the transition state. All right, so once we've formed that transition state, that tetrahedral transition state, We now need to get this reaction to go in a particular direction that moves us towards cleaving the bond. So now essentially what we need to do once we form, so we've split the bond essentially, or I should say, I skipped that, didn't I? Once we form the tetrahedral intermediate, by virtue of having this imidazolium sitting here, right? We move these electrons over here. This splits this bond. Now, because there was a proton hanging out here, right, on the imidazolium, which is perfectly happy to donate back if there's something ready to take it up, and the developing that nascent amine, primary amine on the amino terminal side of the clipped bond is a perfect place for that proton to now come back. So we're doing now an example of some general acid chemistry, and that general acid chemistry, donating that proton from the imidazolium, helps drive this reaction in the direction of splitting the bond, right? So this proton comes back in rather than the electrons going back this direction and then clipping the serine here. This acid donation from the imidazolium helps drive the reaction in the direction of splitting the amide bond. Okay, that's great. We're part of the way now. A water molecule now comes in, displaces the amino terminal side of the peptide, and now all we really have to do is just reverse the steps we just made, right? So here's our incoming water molecule. This is going to let us then regenerate the catalyst and release the C-terminal half of the peptide. Okay. In comes, like I said, our water molecule. Here's our histidine, and now we're going to go through a similar set of steps, right? We've returned back to this neutral imidazolium, right? But now this guy can now act again as a general base, stabilized again electrostatically by the aspartic acid residue, polarize this water bond to generate a reactive hydroxyl nucleophile that can attack the carbonyl. This will regenerate our tetrahedral intermediate, right? You'll recognize this guy again. It pops right back into the oxyanion hole again. And once again, now the imidazolium with the base, or the imidazolium with the proton on it, now can donate that proton back to the serine, right? Regenerating the alcohol in its hydrogen bonded state, and now releasing the piece of the polypeptide with the carboxyl group, regenerating now our starting state of the serine protease ready to go again. And it can execute all of that. That whole series of steps happens, like I said, in a fraction of a second, somewhere in the range of 50 to 100 milliseconds, right? So putting all those ideas together is what makes that happen. Recognizing these fine-grained features of the transition state, dragging down that transition state free energy, lets this reaction go. And remember, thermodynamic driving force for it to go this way is the fact that amide bond is unstable, thermodynamically unstable, right? So the free energy that powers this ultimately comes from the fact that amide bonds have a sort of favorable hydrolysis free energy, but kinetically it doesn't happen, and this enzyme makes it happen. Okay.